In maths, a group is a particular kind of algebraic structure consisting of a collection of elements and a multiplication rule relating them. The group axioms state that all groups have an identity element, inverses, and associativity. This might sound a bit daunting if you've never heard of group theory before, but luckily many groups can be said to act on a set of objects, and this gives us a more concrete way to think about them. Then the group is just a collection of moves that you can do to transform the objects of the set into each other, and the multiplication of two moves just means the result of doing one move after the other. For example, there is a group of four-letter shuffles, or permutations, called S4, and this acts on the set of anagrams of my name, Romy. It also acts on the set of anagrams of my sister's name, Izzy. Alternatively, we could study symmetry groups. Think of the symmetries of the hexagon as the collection of all flipping and spinning movements we can do to a paper hexagon that would leave it looking the same. Every symmetry moves each vertex to another vertex, so we say that the symmetry group acts on the set of hexagon vertices. What are the elements of this group? There's 6 flipping symmetries, 3 like this, and 3 like this, and 5 spinning symmetries, because we can rotate it by 60, 120, 180, 240, or 300 degrees. But we've missed one. The identity axiom says that every group needs to have a do-nothing move. There's a do-nothing symmetry, a do-nothing permutation, and we'll always write it with an E. Here it is. The inverses axiom says that the moves in the group are all reversible, so every move can be followed by another move that cancels it out. The associativity axiom says that moves combine, or multiply, together in a nice way, like this. Just remember, the move that comes first is always on the right. You can't just switch the order. Now we're ready to define some new group theory terms. When a group G acts on a set of objects S, and little s is one of the objects, we say that its stabilizer is the collection of moves in the group that don't change it. The orbit of little s is the collection of objects that it can change into when we do any of the moves in G. To help you remember, the things in the stabilizer stabilize little s, and the orbit of little s is like the orbit of a planet. It shows you where it can move to. That's why we're currently on Mars, by the way. In the anagram example, the stabilizer of Romy would just be the do-nothing element, but the stabilizer of Izzy would contain both E and the move of swapping the middle letters, because swapping the two Z's around doesn't change the word. Now here's a neat result that relates what we've just learned to the group as a whole. The orbit stabilizer theorem tells us that if we know the sizes of any pair of orbits and stabilizers, we can just multiply these together to get the size of the group. Why would this be true? Well, suppose that the group big G is acting on a set big S, and little s is an object in big S. We can draw the objects in the orbit of S as dots, let's say there's n of them, and the moves in the group as arrows coming from S. The moves in the stabilizer, say there's m of them, take S right back to S, like this. All of the other moves take S to somewhere else in the orbit, like this. Now for the fiddly bit. If G takes S to T, and H also takes S to T, then G of S equals H of S, so G inverse H of S equals S. So G inverse times H is in the stabilizer, meaning that H can be written as G times G inverse H, that is, a move in the stabilizer followed by G. Since there's n options, including E, for which move we pick in the stabilizer, then there's exactly n moves to get us to each of the other elements in the orbit. So there's a total of m times n moves in the group, and we're done. Phew. Let's use this theorem to answer a question. What is the number of rotational symmetries of a cube? For a 3D shape, rotations combine to make rotations. For example, if the Earth went crazy and got knocked off its axis somehow, it could be spun back to its original position with just one rotation. Because of this, the group of cube rotations is a group, and it can act on the 8 vertices of a cube. Check the group axioms from earlier if you don't believe me. Look at the red vertex. The stabilizer contains 3 moves, E and the 2 rotations shown. That's 3 in total. For the orbit, see how we can rotate the red vertex to any of the other vertices. So there are 8 vertices in the orbit. Therefore, the orbit stabilizer theorem tells us that there are 3 times 8 equals 24 cube rotations in total. Here are all of them, if you're interested. As you can tell, it would have been easy to miss some if we'd tried to count them all by hand. Now, we can use our knowledge of the group G to answer other questions about the cube. For example, how many essentially different ways are there to colour in the faces if we have n colours available? At first you might say n to the 6, because there are 6 faces with n options for each. But a lot of colourings look the same when you're allowed to rotate the cube, so we've overcounted. The clever approach is to count the number of different orbits when G acts on the set of cube colourings. Because 2 different colourings look the same exactly when they're in the same orbit, i.e. when they differ by a rotation. So we only want to count 1 colouring per orbit. For this, there's a handy formula called the orbit counting formula. Fixed G is the collection of all objects, in this case colourings, that don't change when you apply the rotation move little g. With the bars around it, fixed G just means the number of such colourings. There's a proof of this theorem that this video is too short to contain, but essentially it follows very quickly from the orbit stabilizer theorem. Let's fill in fixed G for each category of rotation we found. When the template uses only 1 colour, there are n colourings that get fixed, so the size of fixed G is n. When the template uses up to k colours, there are n options for each colour, so fixed G consists of n to the k colourings. So the sum is just 1 times n to the 6 plus 8 times n squared plus 6 times n cubed plus 6 times n cubed plus 3 times n to the 4. And for our final answer, we divide by the size of the whole group, which is 24. When n equals 2, plug in the numbers to get an answer of 240 over 24, which is 10. See if you can check this by drawing all of the black and white colourings of a cube. If you do, don't forget that all black and all white also count as colourings. That's all for this video. If you hadn't heard of group theory before, now you hopefully know a bit more of what it's about. Thanks for watching.